final presentation in this section is Dr. Mazlan from Izon Science. Izon has been, for the EV field, I think one of the biggest supporters, both for machines and tools to make life easier, to help improve the reproducibility in the field. So with that, I hand over to you.
Perfect. Thanks. All right, so thank you so much for the organizers for presenting the opportunity to sponsor this event. As Raymond said, we've been long-lasting sponsors of the clinical program. All right, so to start things off, we are not new to nanobiological materials, especially in the nanomedicine field, so this could incorporate liposomes and lipid nanoparticles, or LNPs, extracellular vesicles, as well as viruses and virus-like particles. Now, to kick things off, let's first talk about particle measurement for nanomedicine. All right, so why is characterization important in terms of LNPs or even in EVs, for example, right? So first of all, there is regulatory requirements where size distribution is important, as well as stability, colloidal stability in terms of zeta potential and surface charge are also frequent requirements. In terms of quality control, of course, it's essential to be reproducible in your processes, whether it's isolation or characterization or purification. We also have storage stability, as I mentioned earlier. We have colloidal stability and, of course, aggregation in whatever medium that your nanoparticles will be stored in. Now, last but not least, of course, what's important is the whole track from bench to bedside, where patient safety, of course, is of utmost importance, where size and zeta potential, of course, affecting the safety profile, and the concentration, of course, affects the dosage of what you are going to administer to the organism, whether it's people in preclinical, animals in preclinical or humans in your clinical studies. All right, so this is the current equipment that we have at the moment that utilizes the technology that only Izon can supply, which is tunable resistive pulse sensing, otherwise known as TRPS. Now, the Exoid itself is able to provide concentrations of either size and concentration measurements or size and zeta potential measurements, right? So in terms of the range of particles it's able to analyze, between 40 nanometers to 11 microns due to the numerous types of nanopore types that we have. We have 11 all in total. And to normalize your data, to calibrate your data, not the equipment itself, we do have carboxylated polystyrene particles of known size, known concentration, and known zeta potential to normalize your data. Now, what exactly is TRPS? So TRPS is tunable resistive pulse sensing, and it is based on the Coulter principle. It's an impedance-based measurement, basically. So the consumable that is to be used here is called the nanopore. You can see on the left-hand side, it's made of thermoplastic urethane, and in the middle of the pore, as the name suggests, is a pore of nanosized. So what happens to this is that it will be sandwiched between an upper and a lower fluid cell. There are electrodes, in essence, with a positive in the lower and a negative on top. And what's important here is that your particles have to be suspended in a measurement electrolyte. Now, the importance here is that it has to contain certain ions, because when the voltage is applied to the system, it will create what we call here a baseline current. I don't have a pointer, but you can see that solid purple line on the right-hand side. So that's the baseline current that has been established from the voltage that has been applied. Now, because it's a closed system, and whenever every single particle traverses through the nanopore, it will create what we call a resistive pulse, which translates into a transient blockade of the current that has already been established prior, right? So you could see here by the downward peaks, those are the transient blockades. Now, the magnitude and the amplitude of these peaks relate to the relative size of the particles, meaning longer the peak, the larger the particle, as well as the frequency of which these peaks occur relate to the relative concentration of the particles. Now, I keep saying relative is because we do have, it's important to also for measurements for your calibration particles with known sign, known concentration, known surface charge to get the absolute concentration as well as the particle diameter. Now, I don't know whether those of you in the audience are familiar with this paper. So this was published in 2021 in February, I believe, in the Journal of Extracellular Vesicles, where it pits all nanoparticle analyzers side by side. And numerous varieties of samples were used for this, whether it's polystyrene particles in a polymodel grouping, whether it's liposomes, and whether it's EVs. So here you can see that the strength of the technology actually increases with the complexity of the sample. Here we have polystyrene particles, quadromodel polystyrene particles with 100, 150, 200, and 240, I believe, nanometers. And here you can see where the strength of the technology really lies, where each and every subpopulation is able to be distinguished quite succinctly. Now, because TRPS doesn't rely on optical methods, we don't rely on Brownian motion, you can imagine that with Brownian motion that certain smaller particles can get masked by the larger particles, therefore leading to a loss of either a subpopulation or the multi-populations in general as well, right? So here you can relate to the paper in 2021. I really urge you to read that paper. Now, let's be real also, like in terms of biological samples, we will not have such beautiful subpopulations like this, if those of you who are working with EVs, right? So mostly they're going to be monomodal, they're going to be polydispersed, they're going to be really heterogeneous. Of course, all other techniques are also able to resolve this quite nicely, but if you look at our percentage CV, especially for our EVs from 3 repeated runs of circulating EVs, that our percentage CV is really, really low. And the reason here is because whatever happens to your sample must happen to your calibration beats. There's no going away from that, right? All right, so moving into LNPs here, for example, this is our internal data that's been generated. Here we investigated the difference between mRNA-loaded LNPs as well as empty LNPs. Now here, in terms of size, focusing on size, here you can see that there is an increase in mode for empty LNPs as opposed to mRNA-loaded LNPs, probably to the structural deformation when the RNA is loaded, leading to a complexity of the inner shell of the LNPs. Here now we are going to look at the what happens when you freeze-thaw LNPs, for example. Now here, just looking at mRNA-loaded LNPs against the freeze-thaw process. For the lighter pink population, you can see that after freeze-thawing, there is an elongation of the right tail of this population, which suggests highly aggregated samples as well after freeze-thawing. So it's this kind of intricacies that you can actually detect and distinguish when using TRPS. Apart from showing just a histogram like that, you can either have a percentage population or your concentration versus particle diameter. You would also be able to obtain a scatter plot where you could plot baseline duration, meaning how long a particle takes to be traversing through the pore to be characterized against the particle size itself. Of course, you would expect a linear relationship between the baseline duration and the particle size as it traverses through the pore. But in this kind of plot, you would also be able to determine or to fish out those particles that have maybe an oblong shape, cylindrical shape, where it enters the pore with its smaller diameter, but taking a much longer time to get through the pore, right? So they would probably be outliers. And for example, at the diameter of 100 nanometers, it could take like 90 milliseconds to get through. So this is how you actually fish out for those deformed or elongated or nanostrings, for example. So apart from size and concentration, I mentioned earlier that we're also able to perform size and zeta potential measurements. Now, because the Exoid has a pressure system to allow your particles to go through your nanopore to be characterized, I mentioned earlier as well there are 2 electrodes. Now, for zeta potential, the pressure will be set to 0 because we want to allow the particles to go through the pore based on their own electrokinetic forces, right? So in this way, we are able to determine the zeta potential of these nanoparticles. Now here again, we made the experiment between loaded LNPs versus empty LNPs, and as expected, you see that the pink one, the loaded LNPs, have a much negative charge compared to the empty LNPs. Now, having that said, this is also another paper that was published in 2017 that compares different zeta potential techniques. Now here, highlighting the beige particles, which is the mixed population particles. Right here you have polystyrene particles, carboxylated particles, you have supramagnetic particles conjugated to DNA, and looking at the beige population, we are also able to detect each and every subpopulation based on their charge against diameter sizing, even though they are of the same diameter for different populations. Now, I have like a minute left. I'll go through this really fast. Another part of my technology, of our technology, is actually based on size extrusion chromatography for purification and isolation. Now, for those of you in the know, of course, not much to say about there. We have a porous resin in our QEV columns, and what this allows is to purify your EVs or your LNPs against your decorations or your unconjugated dyes or your unconjugated antibodies. So here, the idea here is not to isolate different sizes of your EVs or your LNPs per se, but to purify them against your contaminants. So for this, for EVs, for circulating EVs, your contaminants could be your lipoproteins. And again, for proteins or dyes. And for your LNPs are your bioactives, your undecorated conjugates, right? So this is how a typical elution profile looks like. So your larger particles, your LNPs, your EVs, will be eluted first in the first few fractions. And you can see the dotted line. These are all your protein contaminants. And in this figure here, it's detected by BCA. So you can also do a simple OD to AT measurement just to see where your contaminants start to seep in. And you can then decide to collect the fractions before to be ensured that you're collecting indeed the purified collection volume. Now, heading into clinical relevance as well, what we are producing now is GMP-ready columns for our larger columns for the 110 and the 2 ml columns. And for us, we all like to cater to scalability. So when I say scalability here, it's in terms of volume. As you can see here, we have all the way from 150 microliters all the way to 100 mLs. Now, normally, we wouldn't produce something that people do not need. So this is all coming from what the requirements in the field in terms of LNPs or excessive vesicles are coming from. All right, so just to quickly go through this as well, this is called the automatic fraction collector. It is just to increase the throughput. It's easy enough to collect your purified fractions using the columns based on gravity. What makes it easier is that you can do it now in an automated and customizable manner, right? Because all of our columns are RFID tagged, you just load them in there, it will already tell you what's the recommended purified collection volume, what's the recommended buffer volume, and you can just press start and it will collect your fractions, as the name says, automatically for you. Just to give you an idea of how scalable we can go to, this is our biggest column that we have. There we have already projects running in America. This is a 2.5 liter column that has been concentrated 25 times. So you can imagine the size range, or the volume range that we're able to go to. Now again, we're also looking for customization, so we'll cater to whatever your needs require. This is an example of what our solution would be for large-scale isolation or purification. It's called a QEV Pure Path solution. It is a solution, it's not a product, and it's three-pronged. First, you have your crude filtration, followed by your TFF, and then followed by your SEC to then obtain your absolute concentration, size, in zeta potential, and your biomarkers before heading to the market. Now, just to end my slides, why the three different components, why the filtration, why the TFF, why the SEC. Now, as you can see here, in terms of purity, by just using TFF, some people do that to isolate, but we realize that when you look at purity in terms of particles per microgram of protein, TFF doesn't improve much significantly in terms of your purity against just pure conditioned media, for example, for bioprocessing. Once post-TFF SEC is being done, you can see the increase in the purity in terms of particles per microgram of protein. Now, with that, I would like to end my presentation. We would love to have an extra discussion with you if you just stop by our booth. We're just outside also. So thank you for your attention.